And then there's my colleague Andrew Zurak, who makes he doesn't use dopants as the qubits, he uses electrons kept inside the nanoscale transistor. So he makes quantum dots, what they're called. They are essentially the super shrunk version of a silicon transistor, shrunk so much that it holds just one electron.
Okay.
So what he does is arguably the most, CMOS similar, CMOS compatible device you can make. It's really just a super small, modified silicon array of transistors. Mm-hmm. And all these three methods have their pros and cons, and we're all making progress, and there's a lot of synergy between
What about
between
non-silicon methods?
Right, so non-silicon methods, some of the two probably most developed and successful ones at this moment are superconducting circuits. Mm-hmm. So that's what Google does, that's what IBM does, and that's what a number of other also smaller groups and companies around the world do. So here you have a circuit that's made from a film of superconducting material. And on this film, you make essentially what is, it's a quantized nonlinear oscillator. So imagine you make an LC oscillator, just an LC circuit, right? It will oscillate at a certain frequency. So if you just take a capacitor and an inductor and you put it here on your breadboard.
It's a tank resonance circuit.
It's a tank resonance circuit. And at room temperature, it will have, billions of microwave photons in it. Yeah. Now, imagine this circuit resonates at 10 gigahertz. 10 gigahertz is the equivalent of half a Kelvin in temperature.
Okay.
Right? So if you now cool down this tank circuit to 20 millikelvin, how many photons are in there?
Zero. Are we talking?
Essentially zero. So it's an electrical circuit, it's an LC oscillator in its quantum mechanical ground state.
Wow, okay.
And then you can introduce one photon in there and it goes in its quantum mechanical excited state. So that's your 0 and the 1. Yep. The problem is you can't just make a simple LC oscillator because then all the energy levels are equispaced. So you don't have only two levels. You have 1, 2, 3, 4. You can put as many photons as you want in there.
Right up to room temperature.
Right up to room temperature, and they're all equispaced.
Okay.
So you need something that is non-linear. And this is done with a superconducting circuit trick. It's called the Josephson junction. It gives you essentially a non-linear inductor.
Got it. That's what they use for the voltage standard, the Josephine junction.
That's right.
Right.
That's right.
Okay.
So you use that principle, and you lay it out in a clever way, and you get what is essentially a non-linear LC oscillator that has the two lowest state with a certain energy difference, and the third state has a different energy gap. So if you apply a microwave photon at this energy, it doesn't then jump up the other level. There's only... And then, so again, for our electrical engineering friends, these are really just quantized electronic circuits, basically. And the way they talk to each other is by either direct capacitive coupling, right? So the capacitances are talking to each other in a Coulomb way, or sometimes they talk to each other by sharing the microwave photon across a resonator. So you can make, if you make a 10 gigahertz half wavelength resonator, it will be about a centimeter long or something. So now you can imagine putting two of these little LC oscillators, non-linear LC oscillator, at the opposite ends of this centimeter long resonator, and these two guys can share a microwave photon which acts as the coupler for them.
Oh, that's interesting.
So you can entangle electronic circuits at centimeter distance via this microwave photon that is shared through the resonator.
Oh, are there practical applications for that?
Well, that's how the most developed quantum computers are built.
Okay, is that like D-Wave? How does D-Wave do it?
D-Wave does it in a different. So the example I gave you is what Google and IBM and some others are using. D-Wave does something different. D-Wave uses what's called a flux qubit. So it's also a superconducting circuit, but you have to imagine it's a loop. It's a loop of superconductor.
A physical wire?
A physical wire, physical loop.
Yeah.
Now, in a superconductor, you can have current that flows without dissipation.
It just flows forever.
So now you can imagine you could encode a 0 or a 1 in the current flowing clockwise and the current flowing counterclockwise. You create some magnetic flux, and in fact, that flux is quantized. It's called the flux quantum. But so if you put a Josephson junction, in fact, 3 Josephson junctions across this loop, you can make a qubit where the current is in a superposition of flowing clockwise and counterclockwise.
Right.
This is another one of the things I love to teach to the students. You know, you cannot take them by the hand and you try to tell them quantum isn't weird, don't worry about it, it's completely not. And then when you really like do it in a lecture style, you come to this inevitable conclusion that there is a current, which is a sizable current, it's like microamps, right?
Yeah.
A current that is in a superposition of flowing clockwise and counterclockwise, which is not the same as saying there is zero current. It's
Right,
not.
no.
It's a superposition of flowing one way and flowing the other way.
And how do they read those?
They read them by essentially making it switch to one side or the other,
Okay.
right? So they can tell whether their current flows clockwise or counterclockwise. And so if you have a superposition, it will project it into one way or the other. It's the same with the spin. If I prepare the spin in a superposition of up and down and I go and read it, I will project it into either up or down. So I will half of the time get the spin in the up state, which escapes, and half of the time the spin in the down state that does not escape.
This is why, and we probably have to get into this now, is why quantum computers, please correct me if I'm wrong, I'm sure I will be, that okay, you've got, you're processing all this information, but quantum computers are really only useful if you get like a single output or a limited output. Is that correct?
Yes. So that is probably the simplest way to understand why is it so hard to make useful quantum algorithms, right? Because so you have this exponential density of information you can encode in the quantum computer, but you can't get it out.
You can only get it out in a limited form.
Yes. So what you need to do is to design an algorithm that converges to a kind of information where the quantum bits are not in a superposition anymore, but they are in a sort of equivalent classical state. One easy example, and I'm going to do some shameful advertising here. I have some YouTube videos myself.
Yes,
There's something called...
I've seen them, they're very good.
Yes, the quantum computing concept. There I show a brief example of the quantum search algorithm. Okay?
Yes.
So that works exactly like that. So let's say you want to search for an item in an unsorted database.
Unsorted is important.
Oh, so if it were sorted, then of course you'll find it.
Yeah.
But if it's unsorted, and the reason this algorithm is intellectually important is because it's one of the very few where we know mathematically that there is a quantum advantage.
Right.
For example, for the factoring algorithm, the famous one, cracked...
We'll talk about that, yep.
We don't know of any way to find the prime factor of a large number in a polynomial time. But there is no proof that this way does not exist.
That's right.
Whereas in the search through an unsorted database, you can very simply prove there is no better option than scrolling to the database. Okay? So if you have an old school telephone book and I give you the phone number of someone and you want to find who is the person who has that phone number, you have no better way than just scrolling through the whole thing until you find the name.
Or you can randomly jump around.
Or randomly jump around, but there's no advantage in doing that.
Yep.
Okay? In a quantum computer, you get there in the square root of the number of steps. So if you have 1 million entries like the Sydney telephone book,
1,000 efforts.
1,000 steps.
On average.
On average, yeah.
Right.
So the way it works is this. You create a superposition of all the entries in the database, and then at every step, at every operation, you do an operation, which I won't go into, but that concentrates the probability amplitude on the item you're looking for, right? So at the beginning, all the entries are equally probable.
Yep.
And at every step, the other ones shrink, and the one you're looking for pops out.
Yep.
So after about 1,000 steps on a million, entries phone book, you will have essentially all of the probability concentrated in the one item you're looking for, and nearly zero everyone else. So now you do a quantum measurement of your register, and with very high probability you'll find, boom, it's in there.
Does
That's
it
the
ever
number
reach
you're
100% probability? In theory?
Does it ever reach 100%? Well, I mean, eventually, if you run the classical algorithm, it will, right?
Right.
So, yeah.
Right. Okay.
Yes.
Got it. That's the answer to that.
Yeah.
All right.
So if you want, if you do 1,000,000 steps, then
Yep.
eventually you're
Yep.
equivalent to the classical algorithm.
Right.
And also there, so in the classical case, we say that the runtime is n/2. So on average, you will scan 500,000 numbers. But if you're unlucky that the number you look for was the last one, then you need to scroll all 1,000,000
That's
of
right.
them. So
It's
just
averages.
on average, it's n/2. On average, it's square root of n. For
So
quantum
the
one.
advantage in this particular case, which is one of the cases that we know of, one of the few, we're going from 500,000 to 1,000. So
Yeah.
what's that?
Yeah, so it's only square root,
Yeah.
you see, so it's not the kind of thing that really changes the complexity class. So it doesn't go from exponential to polynomial. But it's one case where, if you actually look at how it works, it's reasonably simple. And you see really this probability shrinking everywhere and peaking there. So it tells you, also the typical question is, but how do you read out the quantum register if it's got all these superpositions? The point is, a good working quantum algorithm will not have a superposition as an output. It will have a measurable state.
A measurable state.
And that's what makes it hard to develop the quantum algorithms that give you a useful
So even
result.
if we had a quantum computer tomorrow, the algorithms would be severely lacking.
There's a few, like there's hundreds, but
oh, okay.
yeah,
Right,
there's a few hundred.
Okay. Right.
There is a web page that's kept up to date, is the Quantum Algorithm Zoo. And there's some interesting ones like solving sparse systems of linear equations.
Oh, yes.
That's pretty broad.
Okay.
And one thing that's really interesting, I'm just going to tell you this because it fascinates me. I only recently discovered quantum finance.
Quantum finance.
Yes. And so there's various ways in which you can do that. So there are people who are looking into using quantum computers for optimization problems like portfolio optimization, portfolio investment optimization. Basically, you have this much money, and you have some constraints on how many types of different stocks you want to buy. These things become computationally very, very hard very soon, right? And so there are suggestions that quantum computers might be able to run this kind of optimization problems in a more efficient way.
I wouldn't have thought that there'd be a place for quantum there.
No, apparently there is.
Okay.
And the thing that really blew my mind, that I only recently discovered, is that now, I'm not a finance expert, of course, but apparently there is some model whose name I forgot, some economist, who developed a mathematical model for how to essentially model markets in the presence of arbitrage.
Yes.
Arbitrage is when you have, for example, exchange rate fluctuations. So, you buy a TV in Australia, but if you went to buy it in New Zealand, you get some advantage because you made money that way. Yeah. And it turns out, it's amazing. If you look at the form of that equation, it's like the Schrödinger equation of quantum mechanics, where the Planck constant is the degree of arbitrage.
Oh no.
Yeah.
It pops out, does it?
It pops up. So the quantum uncertainty we have in the Schrödinger equation in the economics model is the arbitrage, is the uncertainty in the exchange rates.
Mind blowing.
Right? It's just a mathematical coincidence. There's nothing quantum about the finance, but there's nothing quantum, but it just so happens that the form of that equation has the same form as the basic equation that governs the time evolution of a quantum system. So then if you want to model how will your investment in the presence of arbitrage across different markets evolve in time, you can just as well create a quantum system that is subjected to formally the same equation and watch it evolve.
Interesting.